Good afternoon, everybody. Welcome to the second in the series this summer of the Heidelberg Joint Astronomical Colloquium. And today we welcome another speaker from Australia. Thank you very much for doing this at midnight, your time. That's Ryosuke Hirai. And the host of Ryosuke is Fabian Schneider. I will ask Fabian if he would introduce Ryo. Thanks.
All right, thank you, Richard. And it is my great pleasure today to introduce to you Ryosuke Hirai. Ryo did his PhD from 2014 till 2017 at Waseda University in Tokyo in Japan. And during his PhD times, I think he received a research grant for young scientists in 2015 already. And then he won, I think, one of the most prestigious awards that you can get in Japan to go overseas and abroad. And this one of these overseas research fellowships from the Japan Society for the Promotion of Science. And then he used this fellowship to spend 2 years from 2017 till the end of 2019 at Oxford University. And so he was sort of returning back to England, I think, where Ryo spent a large fraction of his childhood. And that is also where we actually overlapped and got into contact. And then at the end of 2019, Ryo went on as a research fellow, and now he's at Monash University in Melbourne, Australia. And he's also a member of the Center of Excellence for Gravitational Wave Discovery, as you can see on his slide, OSGRAPH. And Ryo has broad interests in, let's say, binary star evolution, binary stars, merging, supernovae, and all sorts of things. And also, I think he's a numerical wizard. And I think you'll see some of these aspects for today. So I'm really happy and excited to have Ryo here. The stage, I think, is yours.
Thank you very much. Thank you, everyone, for joining today. My name is Ryo Hirai, and thank you for the introduction, Fabian. It's slightly unfortunate not to be able to see everyone in person, but I had the opportunity to visit Heidelberg a couple of years ago to the Heidelberg Institute of Theoretical Studies. I had a wonderful time there, so I'm really looking forward, once the borders open up, to be able to visit Heidelberg again sometime in the near future. Today I'm going to talk to you from the other side of the world, about 10,000 miles away, about my work on stellar explosions in multiple systems. And here I have a list of my collaborators in alphabetical order, including Fabian, where we overlapped in Oxford, as he said, and where we spent a wonderful time there. So I would like to start with a brief introduction of the multiplicity of massive stars, which will be the main topic of my talk. So here I've just put several figures of how that indicate how abundant multiple systems are in our universe. So we all know that about half of the stars in the universe are members of binary or higher order multiple systems. But it's also recently being established that the multiplicity fraction is actually higher as you increase the mass of the star. So in the left panel, you can see the fraction of various types of multiples as a function of mass. And for example, beyond 10 solar masses, the fraction of binaries dominate over single stars, but also after 10 solar masses, there's actually more triples than binaries. And if you go beyond, for example, about 20 solar masses, it's inferred that quadruples dominate. So there's lots of these multiple systems in the context of massive stars. And more importantly, these multiple systems or binaries have actually very close orbits that they can interact with each other during their lifetimes. So on the right, I'm showing a figure from a survey of O stars in the local neighborhood, and it's known that about 70% of all these massive stars have a companion close enough that they can interact with each other and undergo these complicated evolutions, for example, by transferring mass to its companion, or even sometimes merging with each other or sometimes not quite merging, but plunging into their star and ejecting the envelope, called the common envelope phase. And these massive multiple systems have attracted wide attention since these high energy phenomena, such as high mass X-ray binaries and things have been discovered. But most importantly, since the discovery of gravitational waves from the coalescence of double compact objects, it has rapidly attracted attention, and more people are working on this in this field at the moment. Here I'm showing a very schematic picture of an example of the life of a massive binary, leading to all the way to the formation of a double compact object, for example, neutron stars and black holes, which will eventually be detectable as gravitational wave sources. And you can see there's many branching points in the evolution. This isn't the full picture, but this is just some examples of some branching points that can totally change the course of the evolution of these massive binaries. For example, there's a star can undergo stable mass transfer or some unstable mass transfer, leading to this phase called the common envelope phase. And depending on how this goes, it can lead to completely different outcomes. For example, just leaving behind a simple binary or leading to a stellar merger into a single object, and so on. There's also sort of interesting things. Each of these panels are standalone areas of interest, areas of research. But my main area of research is in this part of the evolution of a massive binary, particularly these 6 phases. There's some ongoing work in these 4 phases. For example, my student Michael Au is working on hydrodynamical modeling of the common envelope phase for massive stars. And also I'm personally working on creating a new framework for understanding wind accretion in high mass X-ray binaries. But I won't go into detail today, but I want to focus on this phase of a supernova occurring inside a binary system, and also a stellar merger occurring in binaries or even higher order triple systems. So I'd like to start with the first topic of supernova explosions inside binary systems and what we can learn from it. So here is a diagram showing how supernova explosions are classified. So supernova explosions are usually classified depending on their spectral features at the peak of the light curve, and sometimes the light curve morphology, or sometimes even just simply the magnitude at the peak. But these are observational classifications. Theoretically, we can class them into roughly 2 groups, depending on the explosion mechanism, or in other words, the progenitor types. So these top 5 or 6 supernovae are explosions of massive stars going through a core collapse. And there's another type called thermonuclear explosion of a carbon-oxygen white dwarf. We can see for the core collapse type, there's a diversity of spectral features. And this is attributed to the fact that these stars can undergo very different degrees of mass loss before the explosion. And I've ordered it in a way that the top ones have the least amount of mass loss, and as you go down, there's more higher degrees of mass loss, sometimes losing the entire hydrogen or even helium layers of the star. And these bottom 3 are usually grouped together as stripped envelope supernova. Now, there's been long debates of how you can strip off this amount of mass before the explosion, or how you can create these stripped envelope supernova progenitors. And you can group these theories into roughly 2 types. So one invoking strong stellar winds from very massive single stars, for example, like 30, 40 solar mass stars. These stars can have very strong stellar winds, which can shed most of its outer layers, which leaves behind a helium star which can explode as stripped envelope supernovae. On the other hand, you can have binary interactions doing the job. So if you have a close companion star, it can transfer mass and directly strip the outer layers, leaving behind these stripped stars. Now, the way to directly distinguish whether a supernova came from one channel or the other is the easiest way is to just simply find a companion star remaining in the aftermath. And for some supernovae, there have indeed been found some companion stars to these explosions. So I'm showing 4 examples. For example, for a type 1b supernova called 2006 JC, or some type 2b supernovae called 93J or 11DH or 01IG. For these supernovae, a companion star has been confirmed. So in these cases, we are pretty sure that the progenitor was produced through some sort of binary interaction. But this wasn't the end of the story. So if you look carefully at these stars, for example, if we look at the case of 2006 JC, the companion was observed twice. So it was first detected 4 years after the explosion, and the next time 10 years after the explosion, and roughly had the same luminosity. And thanks to the multiband photometry, that we can also constrain the temperature, which can be seen in the right figure in these red contours. The most likely point is this red dot at the right bottom. So we can roughly infer where what the companion temperature and luminosity was just after the explosion. And this is consistent with a 11 to 12 solar mass star in its Hertzsprung gap, which is a very short-lived phase of a massive star. So these blue lines show some example evolutionary tracks of massive stars, and it's known that it spends most of its time in this black strip shaded region on the main sequence, and it shoots to the right side over a couple of thousand years or tens of thousand years, which is much shorter than a lifetime. So it's expected to be quite rare to find a companion in this state. It's still plausible that a companion happened to be there by the time the primary star exploded. But because this supernova 2006 JC and also 93J also had a Hertzsprung gap companion, it's becoming to be in tension with the theory that we expect most of them to have main sequence companions, but we're actually finding about like 2 out of 4 of the known companions in this weird state. So how could this be? So in these inferences, we're implicitly assuming that the star is sort of unaffected by the explosion, but actually the explosion could change its experience in some ways by hitting the other star with the supernova ejector. So for example, if a supernova hits the star, it can actually directly strip off the surface material and change its mass, so it might not be seeing the same mass as it was just before the supernova, or you can just kick it away by imparting some momentum, or more importantly, it can inject some energy into the outer layers of the star and causing it to expand. My research has focused on this phenomenon of the ejector hitting a star through hydrodynamical modeling. So I've developed this hydrodynamical code called HOMO, which has some original features like a very cheap self-gravity solver. But using this, I've simulated the impact of a supernova ejector onto a companion star. And this is just some example movie showing the impact. You can see the star in the middle and the ejector pouring from the top of the panel. And as soon as the ejector hits the companion, it forms a shock that's driven into the star and sweeps through the star. And also you can see the star shock forming. After the ejector passes away, it's heated up and sort of expands a bit. And I did it for various different binary configurations, changing its mass and so on. So here's a summary of the first 2 components, so the strip mass and the impact velocity, which actually doesn't do much. So you can see the strip mass in the top panels, where the strip mass is always below about 1/10 of a solar mass. and I used a 10 solar mass companion, so that's like less than 1% of its mass. So it hardly strips any mass, which is sort of expected because main sequence stars have very tightly bound envelopes. The surface binding energy is quite high compared to the energy injected. And also the momentum imparted is way smaller than the orbital velocity of the star, so it also doesn't do anything for the flow of evolution. So these things are probably unimportant. Also, I also studied the surface pollution. So even though the fast parts of the ejector will just simply flow past the star, the later slow parts that are enriched in heavy metals can partly be accreted onto the star. But even in the closest separations, the amount of accretion is quite minimal. Even at the highest, it's about 10 to the minus 3 solar masses, and it's probably too small that it will be blown away by its own stellar wind in a couple of tens of thousands of years. The important thing is, however, so these things are unimportant, but the important thing is the heat injection. So at the end, the star is injected by some energy of the order of about 10 to the 47 to 48 ergs, which is about 10% of the intersected energy. This isn't large enough to be, like, significantly large enough to be able to strip or ablate the star, but because most of this energy is located in the surface layers, it can actually do something to change the appearance. So in the right panel, I'm showing how the excess energy is located. So this is a function of the mass from the surface, and the excess energy as a function of the mass from the surface. You can see most of the energy is located close to the surface in a very thin layer. So you inject a small amount of energy, but it's also in a small layer, so that layer can be hugely expanded due to the excess heat. And we found that this can completely change the appearance for a while. So this is the longer term evolution after injecting the energy into the star. So we inject, so this is the original position of a 10 solar mass star. And after it's struck by the supernova, because of the excess heat, it shoots up to this much cooler, brighter part of the HR diagram. And this, because it's much brighter and it's much redder, in the optical, this would be much brighter than a normal 10 solar mass star. But it only stays there for a small while because it quickly radiates away the excess energy, and it rapidly shrinks back after a couple of years to a couple of decades. So if we can actually see an inflated state of the companion, and because this inflation is very strongly dependent on the amount of energy injected. So for example, if you fix the explosion energy, it's very strongly dependent on the orbital separation. We can use this observation to infer the pre-supernova orbital parameters. So we carried out a much more wider study to see how the inflated state of the stars correlate to the pre-supernova orbital parameters, or the binary parameters. So in the left, I'm showing a similar figure as the previous figure. So you start with a star here and you strike it with a supernova. It shoots up to the right top corner of the HR diagram, and it rapidly shrinks back. We did it for various mass stars. So this is for example, a 3 solar mass star, a 10 solar mass star, and a 15 solar mass star with different orbital separations. And you can see first, the maximum luminosity achieved is quite independent of how close the orbital separation is. It's only dependent on the mass. So you can actually, if we can see an inflated companion and measure the luminosity, we can use that to estimate the companion mass without any other stellar modeling. This maximum luminosity is actually related to the Eddington luminosity of the star, computed with the ion opacity. So it's kind of physically motivated It's this physical motivated upper limit that the star can achieve during this inflated state. Also, in the right, I'm showing the light curve of this inflated star and the time evolution of the radius. So the bottom panel shows the light curve. You can see that the luminosity stays constant for a long while or for a short while, and then drops significantly after this sort of threshold timescale. It's more prominent in the radius, where it stays inflated for, and it has a constant radius for a couple of years or to a couple of decades, but then it abruptly shrinks back to its original state, more or less like in a step function. So using this, so the maximum luminosity is related to the mass, and the inflated timescale is behaving like a step function and is sort of related to the amount of energy injected. We can actually start using this to infer the pre-supernova parameters. So for this, we created some correlation. We derived some correlations of these things. So for example, the maximum luminosity achieved during this inflated state is a very strongly correlated to the mass, as we saw. So we created a fitting function to this maximum luminosity. So if we can see an inflated luminous star using this correlation, we can actually work back to calculate the secondary mass. And also, if we can monitor the inflated star all the way until it shrinks, then we can use the duration of expansion and this correlation to infer the injected energy. The injected energy is strongly correlated to the orbital separation. So if we can observe a companion star in its inflated state all the way to contraction, we can calculate the pre-supernova orbital parameters to one of the best degrees of accuracy as we can possibly achieve. I see a hand up.
This is Hans Halterix, just a very quick question on the left panel plot.
Yes.
Is there a simple, to which extent does the maximum luminosity not depend on the mass or luminosity that the star had prior to being hit by the supernova?
Sorry, can you repeat that question?
You want to use the maximum luminosity of the star that has been blasted by the supernova as a diagnostic of the supernova precursor. And I was just wondering to which extent I need to know anything about the properties of that star previously.
So you don't need to know anything actually. So the only thing that would possibly feed into the equations is the radius of the star, because the injected energy that we infer from the right panel is related to the ratio of the radius of the star to the orbital separation. So yeah, from the luminosity, we can directly infer the mass. And then from the injected energy, we can only derive a relation between the radius, separation, and the explosion energy.
So for that period, the luminosity of that star is completely dominated by the heating it experienced?
Yes, yes.
Okay, thank you.
Thank you. Yeah, so this is excellent because we can, just from these two observables, we can constrain the pre-supernova orbital parameters quite precisely. We applied this to the supernova 2006 JC. So these blue and orange contours are the positions of the companion star observed in 2010 and 2017. And it's actually quite bluer than the models we computed. So in our models predict that the star should shoot up to this red side of the HR diagram, but the observed companion is actually here. But actually, if the binary survived the supernova, if it didn't disrupt, it can be even if the star wants to expand significantly, it will probably be constrained by its own Roche lobe size, or it will be eroded by the presence of the newborn neutron star. So if we take that into account, we can sort of suppress the inflation. And assuming that we sort of matched our models to be located perfectly within these contours, and from this we can again infer the pre-supernova binary parameters. So from this particular supernova, we expect the companion mass to be 3 solar masses, and this orbital separation to be about 40 solar radii. And this then is very valuable to understand the pre-supernova binary evolution leading to the supernova. For example, if we believe these parameters, it should have gone through a common envelope phase. The companion mass is too small to sustain a stable mass transfer phase, so it should have gone through a common envelope. And the common envelope phase is one of the most uncertain things in binary evolution theory, and we almost have no or very little idea of what the post-common envelope binary separations should be for certain systems. But if we think that this was a post-common envelope system, this binary separation that we infer could be a direct measurement of the post-common envelope separation, and could have some very strong implications for binary evolution theory. The way we could verify this theory is to, first of all, we want to verify whether this companion was actually in an inflated state because of the supernova strike. So we have to see the companion actually shrink back to its original state, and we expect that to happen in the next few years. So we've actually put in a Hubble proposal. We don't know if it will be accepted, but if we can actually see the companion shrink back, then that will verify that this was an inflated star, and probably these inferred binary parameters would be true. I see.
Okay. Go ahead. If you have a very short question, go ahead, please.
Hi, yes, thank you so much. So, very quick question. One thing about 06JC, which I also worked on, was that it had a very strong outburst just 2 years before the explosion, right? So I was wondering, is that included somewhere, anywhere, and the impact on that? Thank you.
So yeah, thank you for the question. Actually, yeah, I'm being very oblivious of this, of the fact that it had a pre-supernova outburst. Actually, we have no idea why this happened. I think nobody actually has a good idea of why this pre-supernova outburst happened, and it's not included in our models either. That's probably another separate research topic that should be pursued. Thank you. Okay, so any other questions?
I think you can carry on. Yeah. Oh, well, can I suggest that we defer the questions for the moment, because there's quite a lot of topics to go through, and then there'll be extended time after the meeting for extended discussions. There's an open-ended Zoom session limit, so I suggest, unless it's something really urgent, that we continue with the main colloquium.
Thank you. Yes, so our models kind of solve the issue of the discovered companions having weird states. So this still, so that means our observations of the remaining companions are still in line with the general binary hypothesis. There's a growing number of supernovae which have actually very strong upper limits on any remaining companion, which is actually against the binary hypothesis. But this doesn't immediately mean that these stars were produced through the single star channel, because there's some other circumstantial evidence that it should have gone through binary scenarios. For example, for this supernova called Cassiopeia A, there's lots of indications that it came from a binary. So Cassiopeia A is this beautiful supernova remnant that you can see in my Zoom background as well. It's relatively young, with an age of about 300 years. We know it's a type 2b supernova because of light echoes. And the ejector mass is quite small, around 2 to 4 solar masses, which means that it's probably impossible to produce a single star channel which predicts much higher ejector masses. We also infer from the X-ray spectra that it has a subsolar metallicity in the beginning, at zero age. I also know the presence of a central compact object. Now, all these evidences support a binary origin in one way or another, but however deep we look around the central compact object, there's no sign of a companion star. In fact, the upper limit is so high that the companion has to be smaller than half a solar mass if there was one, and that's too small to be able to strip off the envelope. So this again is in tension with the general binary hypothesis. Now, we created a completely new scenario that can resolve this issue within the similar kind of framework. So we actually focus on wide binaries that have been generally been left out in binary evolution studies. And we also focus on a mass ratio close to unity binary. In such binaries, by the time the primary star explodes, as a type 2p supernova, the companion star could also be a red supergiant at the same time. And because red supergiants have very loosely bound envelopes, unlike my previous simulations, there's a possibility that it can unbind a large fraction of the envelope and leave us with a stripped envelope star. And at the same time, the binary disrupts because the neutron star is given a kick and also loses a lot of mass, so it's really hard to keep it bound. So we are left with a single stripped envelope star, which can also undergo some winds and pulsations to lose even more mass, and eventually explode as a apparently single stripped envelope supernova. So for this scenario to work, we need to actually know how much of the envelope we can unbind in this process of the ejector hitting this companion. So we did an additional set of simulations with a red supergiant companion instead of a main sequence companion like before. Now, I did some of these simulations in 2014, finding that we can only unbind about a third of the envelope, which isn't enough. But actually, at the time, I was using a general equation of states without the contribution of so-called recombination energy. Now, recombination energy is the energy that's released when ionized hydrogen recombines with the electrons. And using this, we can actually unbind more mass. So without recombination, if you just heat a star, it will just expand and shrink. But if you can expand it enough to adiabatically cool below the recombination temperature, you can inject more energy and send it to escape velocity. So to incorporate this effect, we created a new method to add ionization energy into the equation of state. And we can actually choose the amount of the species of ionization to put in. And, so we did several simulations with different equations of state with different degrees of ionization, or the different species in the ionization. So this is just another movie showing the same thing with the red supergiant. In general, it's the same picture, but we can see a much stronger shock because the envelope is has a much lower density, and it's going through a much more violent interaction. So in the left, I'm showing the time evolution of the bound mass. As soon as this ejector strikes the star, we see a significant amount of unbinding to for example, 4 solar masses for this particular binary configuration. But after a couple of years, no, not after a couple of years, well, yeah, after a couple of years or a couple of months, the recombination starts to kick in and starts injecting energy into the outer parts of the envelope and starts unbinding even more. So if you include helium recombination, that it unbinds a bit more, so as in the red and blue lines. But if you also add a hydrogen recombination, you can also go up to this deep, like in these black lines. So this is for a particular binary, but I've summarized the final unbound mass of these black lines in the right panel as a function of the orbital separation. So the right side of the panel is the more closer systems, and the left side of the panel is the more wider systems. So obviously, the closer you are, you can unbind more mass. And in the most severe case, like in this top blue plot, we can unbind about 80 to 90% of the envelope. which leaves only about 1 to 2 solar masses of hydrogen on top. Now, this is small enough to be able to be blown off by its own stellar wind after being unbound, or through some unstable pulsations and so. So this would probably end up as a type 1b supernova by the time it explodes itself. Or if it's not that close, it will be a type 2b supernova, or type 2L, or type 2p, depending on how much you can strip. So because Cas-A was a type 2b supernova, we can probably this model corresponds to the origin of Cas-A. So our scenario can indeed create a progenitor like it for Cas-A, so that's good news. But how can we confirm this from observations? So this is a general picture that I envision that of the circumstellar material around Cas-A if this scenario was true. So the first supernova in the system occurred about 1 million years ago, which creates a supernova remnant of its own. But supernova remnants are usually only visible up to about 100,000 years, so it's probably very hard to see a 1 million-year-old supernova remnant. The only thing that we could possibly see is the unbound envelope from the interaction. So the interaction strips off the envelope in the opposite direction in the form of a one-sided shell. And if you plug in some rough numbers, it should be located at about 10 to 100 parsecs away from the supernova. We can also look for the neutron star created from the primary supernova, but that's probably hard unless it was a pulsar pointing in the right direction to us. For the case of Cas-A, if we look at the wider region around Cas-A, there's actually this hydrogen cloud located as one-sided shell away from Cas-A. We can see this in hydrogen alpha, and we can also see this in the infrared in this northeast direction. And this cloud is actually located at about 10 to 15 parsecs away, just in the ballpark that we expect this unbound envelope to be. So this could be evidence that the Cas-A progenitor was actually stripped by this first interaction, and this cloud could literally be the smoking gun of this scenario. We found some other supernova with similar features. For example, this one, which doesn't have a companion just like Cas-A, and it has this one-sided shell at about 10 parsecs away from the center. There's another one called G11.2 that also has this 10 to 15 parsec enhancement on one side, which could be the interaction between the supernova remnant and the hydrogen shell. But there's all these supernovas that could have been produced through the scenario, and it could be interesting to follow up to see the other pieces of evidence that could fit into this picture. So a short summary for the first part of my talk. I think I've used quite a bit of time, but I've studied the interaction of supernova ejector with binary companions, which could cause interesting phenomena. If the companion is the main sequence star, it could cause a significant expansion of the star, and we can use the observations of this to infer the pre-supernova orbital parameters that is very valuable for binary evolution theory. If the companion is a more evolved star, it could strip a significant amount of the envelope, and for example, a Cas-A progenitor could have been produced this way. So in the remaining time, I would like to move on to the second topic, which is stellar mergers in multiple systems. Namely, I would focus on this beautiful star called Eta Carinae that you see in this picture. So I've heard that people in Heidelberg are also working on this star. So Eta Carinae is this central star that you see in this picture, which is classified as a luminous blue variable. And it's known to be blowing very strong winds, which is orders of magnitude higher than even the strongest winds from Wolf-Rayet stars, which is supposed to be the strongest wind emitters. And the most remarkable feature is this thing that you see that looks like a sort of snowman, which is called a Homunculus Nebula. The Homunculus Nebula is these bipolar lobes emanating away, from the central star, and it's known to be the result of an explosion that occurred in the 1800s. And at this point, Eta Carinae actually became the second brightest star in the sky, second to the sun. So it was extremely bright, and the energy was comparable to a weak supernova. There's actually some stuff outside the homunculus as well, known as the outer ejector. You see in this red haze around the homunculus, but also this stuff outside that are all moving away from the central star. But actually, these outer ejectiles are moving slower than the expansion of the homunculus itself, meaning that if you traced it back to the center, it had to have been ejected centuries before the Great Eruption. So there had to have been multiple eruptions centuries before the Great Eruption itself. Another puzzling feature is that each ejection in these outer ejectiles seems to be one-sided. So for example, if you look at these blue ejectiles, they were ejected in around 1250, but they had to have been ejected in one direction because we don't see any blue arrows in the other side. Same for the green arrows, so we can only see green arrows in a certain direction, and also for the yellow arrows and so on. So there should have been multiple one-sided ejections with some century intervals for some reason. And last but not least, another important feature is that the central star is not a single star, but it's actually orbited by another star, which is also blowing a strong wind, and the wind from the primary and secondary stars are interacting to cause these very strong X-ray emission, periodic X-ray emission. So there's lots more information that we know about Eta Carinae simply because there's lots of rich observational data because it's so beautiful. I won't go into too much detail today due to the time, but for any theoretical model to be able to explain the origin of Eta Carinae, it has to explain all these features self-consistently. And many models have been proposed in the past that can explain bits and pieces of each of these observational features. But today I'm going to introduce you to our new scenario, or we build upon some of the previous scenarios to produce a consistent framework that can explain most of these features. But in the interest of time, I'm going to draw your attention to three main features. So I'm going to answer what the origin of the strong wind is, and what caused the explosion, and why the homunculus is it's shaped in the shape it is, and what caused the outer ejector. And these 3 points we think can all be explained within this framework of a stellar merger in a triple system. So here is a schematic picture of our whole scenario. It looks a bit complicated, but I'll walk you through. So we start off with a hierarchical triple, which means there's a binary system which is orbited by another tertiary star on a wider orbit. They all have similar masses, so they're quite stable and for a while, but at some point the primary star starts to transfer mass to its companion, and due to angular momentum conservation, it should widen the inner orbit at some point. If the orbit widens, this ruins the hierarchy of the orbits, causing the orbit to become quite unstable. And this destabilized system can cause the inner stars to actually encounter each other to very close separations and sometimes graze each other's surface. And this grazing of the surface could, we think, could cause some mass ejections in confined directions, which we think is the origin of the outer ejectiles. But at some point it becomes even more unstable, it's totally chaotic, and then leads to a stellar merger of two of the components. And during this merger phase, it goes through a common envelope phase where the cores of the two stars orbit within the common envelope, and eventually the two cores will coalesce at the center, releasing the last bit of energy and angular momentum and causing an explosion that we saw as the Great Eruption. But the explosion isn't enough to bind the whole envelope, so most of the mass is contained within this merger product. But this merger product contains a huge amount of excess angular momentum and excess energy. And we think this will drive a super Eddington wind in a bipolar manner. And this will sweep up the inner parts of the ejector into the form that we see as the bipolar Homunculus Nebula. So this is our picture, and just want to briefly show some theoretical calculations we did to verify this scenario. So for the first half, we carried out some dynamical calculations of the triple evolution. So here I'm plotting the distance between the two inner stars as the blue lines, and the outer star and the inner star as the red line. And you can see for a while the triple is quite stable, and the distance between the stars doesn't change too much. But at some point there's some secular instability that builds up, and the two stars approach each other to very close distances with 100-year intervals. And at some point it becomes even more unstable, causing the system to become very chaotic, as you see in this movie. And it can experience some swaps of the companions and all sorts of crazy stuff. And in the end, two of the stars approach each other and merge. In this particular model, the post-merger system has an eccentricity of 0.9 and the orbital period of 7 years, which is very close to the observed value of the current day binary orbit of Eta Carinae. We also simulated the response of the surface material to close encounters in eccentric orbits. I'm showing the movie of a close encounter with different eccentricities, and you can see beyond some threshold eccentricity, when the eccentricity is high enough, we can see some ejectiles being shot out in a certain direction. If we record the direction of the ejectiles being shot out, we can see that it's shot out in a confined direction with a 90-degree opening angle along the orbital plane. So if we think that this close encounter happens every 100 years in that modulation of the triple evolution, it can create this messy structure outside. So if we combine this calculation with the previous triple calculation to estimate how the outer ejectiles should be located outside the homunculus. And this is what it looks like. So the homunculus is this red and blue thing, and you can see that the outer ejectiles should be located in this sort of a tilted torus form, and that's not aligned with the homunculus equator or anything. But more importantly, if we look at this structure from the direction we see Eta Carinae today, and color them according to their ejection dates, it has a very qualitatively similar distribution to what we observe around Eta Carinae. So these calculations give us hope that our scenario kind of works, for at least for the first half. We also went on to do some calculations for the second half of the merger itself. So I'm not going to go into detail, but we created a common envelope and then injected energy in the middle to express the final coalescence of the cores. And we found that it causes these bipolar explosions at first, but eventually the shock penetrates the equator as well and causes this rather spherical explosion that doesn't look like the homunculus. But again, the merger product is left with a huge amount of excess energy, which should blow a super Eddington wind from inside. So we simulated the interaction of the wind with the inner parts of the ejector, like this, and we can see that the wind sculpts out the inner parts of the ejector into this sort of bipolar homunculus-like shape. And if I skip a bit, yes, so at about 160 years, which is roughly the day today, the size and shape of the homunculus of our shell is very similar to the size and shape of the homunculus that we see today, indicated by these white dashed lines. So this kind of also verifies that our merger scenario is capable of producing the morphology of the Homunculus Nebula, and which gives a nice comprehensive picture that fits supports this triple merger scenario for Eta Car. Now, the reason why we care about Eta Car in the first place is, well, first it looks fascinating, but also we can use this rich information of Eta Car as a prototype of stellar mergers inside multiple systems, because a lot of the massive stars should reside in these triple systems. So using Eta Car as a prototype, we can understand the physics of stellar mergers and possibly triple evolution, and then we can use that knowledge to draw analogies and understand the formation of other objects that could have been produced through these channels, such as B-E stars, or possibly these interaction-powered supernovae. For example, as I think Mariam asked, the origin of the outburst for 2000 JC, that could have been a merger being followed by a supernova, but we don't know, but we can possibly use the knowledge gained from Eta Car to be able to use it to infer the formation of these other astronomical objects and phenomena. So I'll leave my summary up there, and yeah, I'll finish my talk. Thank you for your attention.
Well, thank you very much, Rio. This was a fascinating talk, and it looks like it's going in a whole load of new directions, and I'm sure there's lots of questions. We'll have an extended session for questions moderated by Fabian Schneider after the main session, but for the moment, I'll take 2 or 3 questions from the floor. Hans Walter Rix, I think, wanted to come in with one. Is that right?
No, I got to ask my question. I should let others go first. If there's time at the end, I'm happy to.
All right, then I'll ask Mariam Modjaz to kick off with the questions.
Yeah, thank you so much. This is a really wonderful talk and very, very important work, of course. So in terms of Cassiopeia, so it's very interesting. So you're saying this Cassiopeia was the second supernova in the system, yes. Right? And yes. So yeah, so there have been also research on trying to find the companion, and it has been fruitless. But you're suggesting it already went supernova, right? That's yes. What we don't see any supernova. So that's very interesting. So that's very interesting to have another way of producing the stripped envelope supernova that Cassiopeia was. But wouldn't that increase the rates too much? I mean, we already have so many stripped envelope supernova in some ways, right, from the rates. But if you had now another way of making them by just the companion going through supernova stripping in, is that fully consistent yet?
Yeah, so that's an excellent question. So I had this backup slide to talk about the rates. Yeah, so thanks for the question. So the only conditions we need for my scenario is that the orbit has to be wide enough, but not too wide, so that we don't have any stripping. So the orbital separation has to be in this sweet spot with this indicated by this pink stripe. But also the mass ratio has to be quite high, because the secondary has to be in the red supergiant phase to be strippable. Mm-hmm. Otherwise, main sequence stars don't have any effect. Mm-hmm, mm-hmm. So combining these two conditions, actually we can only produce about 0.5% of all core collapse supernovae go through this. So it's not too much for rates. So it can only be a small fraction of the type 2Bs. Mm-hmm. But then it becomes, we can ask the question whether the best known type 2B supernova, so Cassiopeia is probably one of the best known, but would that come from one of the rarer channels? I'm not sure. That's another question that I would like to pursue.
Okay, thank you so much.
Thanks. Any more questions from the floor at the moment? Don't see one for them. Yep. So Friedrich Roker.
Yes, thanks for the very nice talk. I have a question related to the supernova companion star interaction models that you did. So similar models have been considered for the progenitors of type 1A supernovae. And so you talked about the energy deposition and the expansion of the companion star. But what happens actually first in the interaction is that you drive a shockwave through the companion star, and people have looked in the, Dan Kaysen has looked into this in 2008, I think. And the finding there is that this shockwave actually gives rise to perhaps a UV flash or some early bump in the light curve that you would actually see directly associated to the early part of the supernova observation. So is that also expected in your scenarios, and have there been such observations?
Yeah, so yeah, that's very an important point. So this has actually been studied more carefully by Dan Kaysen, but also Takashi Moriya. And for this UV flash to be observable, we have to be looking at this bow shock from the right direction. And this reduces the number of opportunities to be able to see a UV flash, in addition to be able to see the early parts of the supernova light curve anyway. And I think based on his calculations, the rate of being able to observe such a UV flash for type 1b supernova was quite low. I don't remember the numbers off the top of my head, but it was like a once in a lifetime thing, I think.
Thank you. I have a question, if I may. I'd like to come on to Cassiopeia, and you mentioned that in your scenario,
Yep.
the second supernova
Yep.
would happen in a rarefied volume caused by the relaxation of the primary. Sorry, of the second. Sorry, the second star whose outer layers were blown away would relax and emit more energy, causing some sort of a rarefied volume into which the secondary would explode, which exactly fits what we know about the dynamics of Cassiopeia. My question is, you know, the red giant evolution prior to that sort of hot wind right at the end would itself give a shell of material, maybe of order a parsec away or something like this. And okay, correct me if I'm wrong.
Sorry, yeah. So so the secondary supernova, the progenitor of the secondary supernova used to be a red supergiant about 1 million years ago.
Right.
Up to the point the first supernova happened.
Right.
So any traces of this wind from would have been wiped out by this first supernova, and we're only left with this shell from the interaction, but also the fast wind from what was left after being stripped. So it would probably be really hard to find traces of when it was a red supergiant.
Oh yeah, I mean that was my question, because you know that there's a lot of mass out there in that red giant ejector from before any supernova happened, which would presumably limit the size of the supernova remnant. So I was just wondering if you predicted any asymmetry in that distribution of the target material. Second supernova, whether that would still be visible within a few parsecs away.
Yeah, so the scale of this this red thing is about 10 to 100 parsecs. So the red supergiant phase stuff should have been even larger, which probably dissolved into the ISM already. So it's probably hard to find.
That's probably too far away to say very much. Okay, thanks. Final question before we stop the main session from Ralph Klessen.
Okay, thanks, Ryosuke. This was a fascinating talk on a really cool topic. I learned a lot, but I have, I guess, a rather technical question. I mean, modeling the interaction of radiation with the wind or the collision of two winds is numerically extremely demanding. So I'm wondering whether you could say a bit about the numerical requirements to reach convergence and to really get the result out that you got? What do you need to do to get a converged result?
So actually, from our case, we only did like just simple hydrodynamical simulations. So we didn't like properly model the wind driving or anything. All we did was solve the hydro equations with radiative cooling, with some sort of cooling function. So in that sense, it's not particularly computationally demanding at all.
There he is again.
Okay.
Hi, Rio. Do you want to finish that question from
Yes. Sorry. How far did I get? And didn't.
I think you just said it's pure hydrodynamics. So I guess it's mostly ballistic motions then, right?
Yes, with some radiative cooling. So it's not radiation transport. We did put in radiative cooling with some cooling function taken from some studies of these cooling functions from various people. But yeah, otherwise it's just pure hydro, so it's not too computationally demanding. So
yeah, that makes it easier.
Okay, well, that concludes the main question and answer session. We'll continue later. I've just explained, Rio, that we're going to continue with you, thanks to your kind offer to stay around for further discussion. Before we thank our speaker, I'd like to make one further announcement. So I will just take the screen briefly. Screen share, and it's my one, and I'll just put that up there. So I'd like to announce next week's colloquium in advance. We're going to go into what is one of the main themes of this series, which is black holes and their effect on many things, and we're glad to be able to welcome next week Susanna Alto to talk about ULERGs and some of the latest information coming from parsec resolution, HST, and ALMA observations of the nearest supermassive black holes in these objects. So that was next week. I can hand the screen back, and I would just like to invite everybody to open up their microphone and video to thank Rio for this really absolutely fascinating and intriguing view into what looks like a new field of research to me, at least as a layperson. Thank you.